Unit 2, Lesson 2, Introduction to Trigonometry. Let's talk a little bit about vocabulary first. We've got different types of triangles. Sometimes we classify triangles by sides, and sometimes we classify triangles by angles. The first type of triangle, if we have three sides that are the same, we call this an equilateral. So, by definition, an equilateral triangle is special because we have three sides are the same. Now, when we have a triangle that has two sides that are the same, this is called the isosceles. And the key takeaway point here is we have two sides are the same. Incidentally, if I am talking about an isosceles triangle, we're also going to have two angles that are the same as well. The third type of triangle that we have, talking about sides, is where we have one that have no similar sides. And we would call this a scaling triangle. We can talk about triangles by classifying it by their angles. So if I have a triangle where all the angles are less than 90 degrees, we call this an acute triangle. So let's write our definition. This is all angles are less than 90 degrees. We can have an obtuse triangle. An obtuse triangle would mean that we have one angle that is greater than 90 degrees. Last, we have a triangle that has a 90-degree angle, and this is our right angle triangle. Key factor here is we have one 90-degree angle. Hey, let's recall Pythagorean relation. Pythagorean relation states that if a squared is added to b squared, this is equal to c squared. Now let's give some definitions. We have a and b are sides that touch a 90-degree angle. C is the side across the 90 degrees. We can also call this the hypotenuse. So whether we call this A or whether we call this A, they're interchangeable as long as it touches the 90 degrees. Now, what it's saying is that if we take the sum of the squares of the two sides, this will add to the square of the hypotenuse. Okay, so let's use Pythagorean relation to find the missing side. We have a side 4, a side B, and a 7. So I know that 4 is equal to my A side. B is my B side, and C is going to be 7. Now I can use Pythagorean relation to solve it because I know that if I have two sides, I'm always able to find the third side. So we do 4 squared plus b squared is equal to 7 squared. Let's continue to simplify. So I have 16 plus b squared is equal to 49. B squared is equal to 49 minus 16. Let's move this over here. And we have b squared is equal to 33. We need to undo the b for us to find the b squared, for us to find the side b. So the opposite of square is the square root. Let's put a little note here. Okay, so to undo the square, take the square root. Right, our next example, we have a triangle with sides C, 5, and a 9. Now, don't be deceived. Sometimes we have a side C, but it really isn't side C. Because this is touching the 90-degree angle, it doesn't matter what it's labeled as. We have to count this as either an A or B in my equation. So really, my C in this case is equal to A. B is my 5 centimeters, and we have C is equal to 9 centimeters. Now, when I substitute it into my equation, I'm going to have A squared, oops, A squared, no, A squared plus 5 squared is equal to 9 squared. A squared is equal to 81 minus 25. A squared is equal to 56. And we are going to undo it by taking the square root. And we have square root of 56. Now you could take your calculator and get the square root of 56, but it's probably going to be a decimal answer. So if we keep it as a square root, then we don't have to talk about rounding. This is the most accurate answer that you could have. Now let's talk about labeling a right angle triangle when we're talking about trigonometry. We already said that if I have two sides and I want to find the third using Pythagorean, I can say that A and B are the two sides that are touching the 90 degrees. Now we're going to be a little bit more specific when we're talking about labeling a right angle triangle for trigonometry, because we have something called the working angle. The working angle, like the name suggests, is what we're working with. So I have A as the working angle of the lower angle on the right. We know that the side across from the 90 degree is our hypotenuse, and we had this from before. Now, our other two sides will depend on where the working angle is. So since the working angle is down here, the side that's across or opposite of the working angle is called the opposite. And we have the side beside our working angle and the 90 degrees. This is called our adjacent. Now, mathematicians aren't really all that original. We called the opposite side the opposite, and we called the adjacent side adjacent. Let's try another one. This time, the working angle is the upper angle. The side across from the 90 degrees is always our hypotenuse and probably the easiest one for us to recognize. Now, we need to look at our working angle to determine our other two sides. We have an opposite and an adjacent. So across from the working angle, we have the opposite. I'm going to put a definition here. Across from the working angle. And we have the adjacent right here. So this is the side between the 90 degrees and working angle. Okay, so pause the video now and answer this on your own. Right, here's the answers to the slide. Right, so let's continue on with the lesson. We're going to investigate primary trig ratios here. What we're going to do is we're going to talk about the ratios when we're comparing sides. First, we're going to write it as a fraction and then a decimal. So the first ratio that I'm interested in is to write the ratio for opposite over hypotenuse. Now I'm working with this 53 degrees. That means that my 1.5 is the opposite, the 2 is my adjacent, and 2.5 is my hypotenuse. Similar with triangle number 2, I have the adjacent, opposite, and hypotenuse. Okay, so in triangle 1, opposite over hypotenuse, we have 1.5 over 2.5. It calculates it for you. As a decimal, we have 0.6. In triangle 1, adjacent over hypotenuse, 2.0 over 2.5. We have 0.8. And then the last one, we're going to take opposite and put it over the adjacent. So 1.5 over 2.0. Let's do this again for triangle 2. Triangle 2, opposite over adjacent, 3.0 over 4.0. Or sorry, opposite over hypotenuse, that's 5.0. So 0.6. Next, we have adjacent over hypotenuse, 0.8. And the opposite, we have 3 over 4. Now look at all of these ratios in decimal form. You'll notice that opposite over hypotenuse in triangle 1 is exactly the same as triangle 2. Similarly, in all of the other ratios, we have the same numeric value. So what that means for both of these is that these triangles are in proportion. So these two triangles are similar. Okay, let's discuss what the primary trig ratios are. In similar triangles, the ratios of the side length, opposite, adjacent, and hypotenuse are proportional. These ratios occur in relation to an angle of reference, or a working angle. You'll often see this symbol, theta, for angles, or you might see some other Greek letter, but in math convention, normally you do see Greek letters referring to angles. Now, you cannot use the 90-degree as your reference angle. You might have heard of Sohcahtoa before. Sohcahtoa is a memory trick to help you remember the primary trig ratios. So, the reason I say it's a memory trick is because the first letter of each of these segments represents sine, cosine, and tan, which are the primary trig ratios. Now, the second and third letter tells you what the ratio is. So first of all, we have sine theta, so sine of an angle is equal to opposite over hypotenuse. So first I have S for sine, O for opposite, and H for hypotenuse. My second primary ratio is cosine. So cosine of theta is equal to adjacent over hypotenuse. And once again, this memory trick here, I have C for cosine, A for adjacent, and H represents hypotenuse. Finally, we have TOA, and that is for my tangent. Tan theta is equal to opposite over adjacent. So T for tan, O for opposite, and A for adjacent. Let's do an example here. We're given the triangle JED. Find three primary trig ratios for angle D. Leave them as fractions in simplest terms. So first of all, for us to find the primary trig ratios, we need to have all three sides. We're missing side EJ. Let's use Pythagorean relation to solve. So Pythagorean relation says I'm going to take my two sides that touches the 90 degrees, square them and add it up, and it's going to be equal to the third side squared. So I have 24 squared plus JE squared is equal to 26 squared. Let's expand this now. So 24 squared, we have 576 plus JE squared, and this is equal to 26 squared. Let's rearrange our equation. JE squared is equal to 676 minus 576. JE is equal to the square root of 100, and we have the side JE is equal to 10. Okay, so let's find the trig ratios now. I'll write down the memory trick. We have So, Ka, and Toa. And we want to find this for angle D. So that means angle D is our working angle. So sine D is equal to opposite over hypotenuse. So opposite is 10, hypotenuse is 26. Let me simplify this into simplest terms. So because both of these numbers are divisible by 2, I'm going to make it 15 over 3. Next one, cosine of D. Cosine is adjacent over hypotenuse. So adjacent is 24 over hypotenuse of 26. And when we simplify, we have 12 over 13. Finally, tangent. That's equal to opposite over adjacent. So we have 10 over 24. And we simplify that to 5 over 12. Okay, another example, we're going to do something very similar. Given the triangle HUG, find three primary trig ratios for angle G. So we know that angle G is our working angle. Round your answers to 4 decimal places. We only have 2 sides, so we're not quite able to find the trig ratios yet. Let's use Pythagorean relation to help us solve. So we have 64 plus 225 is equal to GH squared. GH squared is equal to 289. Let's take the square root of that, and we have GH is equal to 17. Now, I was able to do that one in my head, but if you can't, go to the calculator and punch it all in. Right, so our primary trig ratios. Sine of G is equal to opposite over hypotenuse, 8 over 17. Let's make this into a decimal. So we have 8 over 17, and we're going to take the first 4 digits. So we have 0.4705. But since our 5th digit is a number greater than 5, we need to round our last digit up. I'm going to write this is equal to 0.4706. Next one, cosine G. Cosine is equal to adjacent over hypotenuse. So we have 15 over 17. Let's type this into our calculator, and we have 0.8823, and the digit afterwards is a 5. 5, we're going to round the last digit up to a 4. 0.8824. Finally, we have tan G, and we're going to use opposite over hypotenuse, 8 over 15. And we have 0.5333. Okay, so pause the video, try this on your own. Right, this is the solutions to the question I asked you to try. Right, so I'm going to do another example now. In this question, we're not given a picture of the triangle. Instead, I've given you a description of what this triangle looks like. We're going to have to draw it and then find the sine and cosine of the working angle. So in triangle XYZ, we have y is equal to 90 degrees, xz is equal to 10, xy is equal to 5, and yz is also equal to 5. So let's draw a triangle. I know that there's a 90-degree angle, And they've told us that 90 degrees is labeled as angle Y. Angle X and Z, we'll just place it at one of the other two angles. And we know that side XZ is 10. So XZ, our hypotenuse, 10. XY is 5. And our last side, YZ, is also 5 centimeters. Let's find sine Z. This is our working angle. We're going to look for the opposite over hypotenuse. So I have my 5 over 10. Sine Z is equal to opposite over hypotenuse. And we can simplify that to sine Z is equal to 1 over 2 or 0.5. Right, the second part, we're asked to find cosine X. Cosine X, this is now our working angle. And we're looking at adjacent over hypotenuse. Cosine X is equal to 5 over 10. And we can simplify that to cos X is equal to 1 over 2 or 0.5. Now you'll notice that these ones just happen to be exactly the same. So what that tells us, because we've got two sides, this is an isosceles triangle. Let's do one more example here. We have triangle AB and C. AB and C, we know that B is equal to 90 degrees, AB is 8 centimeters, and BC is equal to 6. Let's draw a triangle. The 90-degree angle is labeled angle B. I'll put A here and C here. AB is equal to 8 centimeters, and BC is 6 centimeters. Now, for us to find sine A and cosine A, we need to have the hypotenuse as well. So let's use Pythagorean relation to help us find side AC. We have 6 squared plus 8 squared is equal to AC squared. So 36 plus 64 is equal to AC squared. We have 100 is equal to AC squared, and we're going to undo AC. AC is equal to square root of 100 or 10. Great, now we're able to find our sine and cosine of A. A is our working angle. So we have sine A is equal to the opposite over hypotenuse, 6 over 10. Let's simplify that. So sine A is equal to 3 over 5 or 0.6. And our second one, cosine A, is equal to adjacent over hypotenuse, so 8 over 10. Let's simplify that. So cosine A is equal to 4 over 5, or we could say 0.8. Okay, the next 3 slides are some questions for you to try on your own. Actually, just 2 slides. Pause the video and try those. I will put the solutions up. Right? Solutions to questions for you to try. This is the first one and the second slide. Right, so that's the end of Unit 2, Lesson 2.